Hi, this is the second video that we're using for section 5.1, where we're looking at distributions of a function of a random variable. If you remember where we're working in a situation where x is a continuous random variable with probability density function given by f sub x of little x. And we've been working in the situation where y is a function of x and has its own probability mass function. Sorry, should be probability density function because we're working continuous here, which would be f sub y of y. So last time we saw how to use the distribution function technique to find the probability density function of y. This time we're going to see another technique called the change of variable technique, which we can use as sort of a little bit of a shortcut to the distribution function technique. And we can use it when our function of x, y, is either strictly increasing or strictly decreasing. So we're going to look at two cases. We're going to look at the case in which the function is increasing and the case in which the function is decreasing. And then we're going to sort of generalize our rule here. So the first case, y is equal to a function u of x, which is a continuous increasing function of x, with an inverse function given by v of y equals x. So that's our inverse function to go back from y to x. So if we think about finding the cumulative distribution function of y, this is the probability that y takes on a value less than or equal to little y. And it's also equal to the probability that u of x then is less than or equal to little y, which, because we have an inverse function here, is equal to the probability that x is less than or equal to the inverse v of y. Now we can find this using the cumulative distribution function for x. We'd integrate from the lower, and so we should say x is defined on the interval c1 to c2, so whatever those values are. So it'd be the integral from the smallest possible value of x up to v of y of our PDF for x, which the fundamental theorem of calculus tells us is equal to the cumulative distribution of function of x evaluated at v of y minus the cumulative distribution function of x evaluated at c1. But we know that x can't take on any values less than this, so this part goes away. So we have f y. Okay, so we have now written our cumulative distribution of function of y in terms of cumulative distribution function of x. If we want to find the probability density function of y, we can take the derivative of its cumulative distribution function of y, which is the derivative of the cumulative distribution function of x evaluated at v of y. And if we use the chain rule, we can also find that this is equal to f of v of y times v prime of y. So this gives us a way, without sort of, if we look at it, we can say, okay, if we know the distribution function of x and we know the inverse function of y, it gives us a way of calculating the probability density function of y without having to actually go through this process of integrating, right? Which is what we did when we used the cumulative distribution function technique last time. Okay. Now the second case that we're going to look at is when the function u of x is a decreasing continuous function with an inverse v of y, but now we're decreasing, so this is the only difference here. So again, we're going to start by focusing on the cumulative distribution function of y. This is the probability that y is less than or equal to y, which is equal to the probability that u of x is less than or equal to y. And now because this function u of x is decreasing, this is actually equal to the probability that x is greater than or equal to the inverse of y. So here, this is going to be the integral from v of y to the largest possible value that x could take on, C2, of our PDF of x dx. Once again, the fundamental theorem of calculus tells us that this is f of C2 minus the antiderivative v of y. And because this is the cumulative distribution function of x, this is the largest possible value of x, we know that this must equal 1. If we want to find the probability density function of y, we're going to take the derivative of fy of y. When we take the derivative here, derivative of 1, this goes away, we get negative f sub x prime of v of y times v prime of y. And notice that this is going to be negative because we've got a decreasing function. So this could be rewritten as f sub x prime of v of y times the absolute value of v prime of y. Because we've got a negative and a negative, positive. Okay? So, in general, the change of variable technique is to find the distribution function of y. We can take the distribution function of x, evaluated at the inverse of y, and then take the derivative of the inverse of y with respect to y, and then take the square root, the absolute value of that and multiply the two. And this works if u of x is either an increasing or a decreasing function, and we have to pay attention to make sure that we specify the support of y. Because it may be different from the support for x. Okay. So we'll take a look at two examples. These are actually the same examples that I did last video, where I used the distribution function technique. We'll solve the same examples, but using this new change of variable technique. So the first example, if you recall, was that we have a random variable x with a probability density function 3x squared on the interval from x equals 0 to 1. and we had the function y equal to x squared, which means that our inverse function, if we want to isolate x is equal to the square root of y. So our v of y is the square root of y here. So now, using our change of variables technique, we're going to say, okay, PDF of y is equal to f of x evaluated at the square root of y, it's our inverse function, times the derivative with respect to y of our inverse function, square root of y. So what this gives us is it gives us 3 times the square root of y squared. Our derivative over here is 1/2 times y to the minus 1/2. And multiplying our exponents here, we get 3/2 times y to the 1/2. And I need to specify my support. Since x went from 0 to 1, y equals x squared. It's going to go from 0 squared to 1 squared. So y also is on that same range. And as you recall, that's the same answer we came to last time, but this was a little less involved, a lot easier. This is kind of a shortcut. Example 2 from last time. Here we've got the decreasing function, y equals negative x squared. We've got x with a uniform distribution equal to 1/2, the interval from 0 to 2. Right away we're going to notice that if I take 0 squared, that gives me 0. If I take 2 squared, that gives me 4, but it's going to be negative, so I'm going to be on the interval from negative 4 to 0. It's going to be y. Now if I want to find the probability density function for y, again, I'm going to need the inverse function. So solving here, x equals the square root of negative y. So our v of y equals the square root of negative y. So I'm going to take my probability density function of x evaluated at v of y, so negative square root of y, times, I'm going to take my absolute value of my derivative of square root of negative y. Evaluated at y equals negative, at the square root of negative y, I get 1/2. I'm going to multiply that by the absolute value of negative 1/2 times minus y to the negative 1/2. Which, if I simplify, gives me 1/4 times minus y to the negative 1/2. Again, the support of y is from negative 4 to 0. And this is the same answer that we came to last time using the cumulative distribution function technique. This time we used a simpler technique. It was a little bit less involved. And this sort of shortcut works any time that we've got a function that is continuous and strictly increasing or strictly decreasing and invertible. Okay? Hopefully this helps you get started using the change of variable technique. Have a good day, and I will answer any questions you have if you post them on the discussion board or send me an email. Thanks.